Please wait.
Just a few minutes. Sir is going to join.
Okay, ma'am. Good evening.
Good evening, Amma. Good evening. Sir is also coming. Okay.
Okay, ma'am.
Okay. Yeah.
Good evening, sir.
Hello, good evening, everyone. Can you hear
Good evening,
me?
sir.
You're able to hear me, no?
It's some writing, sir.
Yeah. Sorry for the delay. Yeah. Okay. Uh, Last time we have seen um, some of the topics, and I have given the notes as well. Okay. So today, what we do is last time just a quick review of what we have done, and let's continue with what we are doing. We have done, for instance, the career concentrations, career concentrations of electrons, holes. Okay. First time when you are listening to this kind of derivations, okay, looks somewhat difficult. But if you are from electronics background, yeah, and these things are not new to you, okay. And the other thing is that even in electronics paper, you have this concentration of electrons calculations, okay. So that you can make use of in the subjects. So that's about that. And all you need to do is to go ahead with the step-by-step procedure. As I said, so you don't have to remember all the 20 steps or something, but instead the highlighted ones, whatever I said, only a few steps that are must be remembered. So there's no time. We are not finding the reason why we are writing, for instance, NH we are writing, okay, for Z of P we are writing, okay, for P we are writing. So those things you don't have to worry about. Only thing is that it starts from those equations, and those equations you have to continue writing so and practice them. Okay, and then it will be easier. Okay, so as for our discussion further, we have what we do. We will go for the lasers. Yeah, lasers also one of the important topics, and those topics will be quite helpful and will be quite useful. And also, the important thing is that they are quite easy and they can score marks. From the examination point of view, I don't want any student to miss any questions from lasers. Okay, that's how you have to decide. Okay, that's how everyone must be in a question because lasers is one of the easiest topics, so rather compared to some other topics, so quantum related topics. These lasers are quite easy, so you should take this as an opportunity. Okay. First, to begin with, we talk about lasers. Okay, so introduction to the lasers, what the lasers are. Okay, and the laser properties, laser characteristics. We will try to understand. Okay, and the applications. Okay, in the medicine and also in the defense. Okay, there are many applications, of course, okay, with the lasers and the production of lasers. Kind of okay, how the optical pumping metal states. Okay, what are the metal states? So this population inversion. Okay, optical pumping and the methods of production of laser. Okay, so these are the things you have it in your laser topic. Okay, first of all, to begin with the history of lasers. Okay, history of lasers actually dates back to 1917 when Albert Einstein has first identified theory, okay, which makes lasers possible. He actually proposed theory, and later on it is called stimulated emission. Okay, so I'll tell you first of all laser. Laser, LASER, laser. Laser stands for light amplification of stimulated emission of radiation. Light amplification by stimulated emission of radiation. Light amplifies. Amplifies means it is increasing its intensity. Okay, light is getting increased. The intensity has been getting increased and it goes off in the form of radiation. Okay, so that means, in other words, you can say that is an enhanced intensity. Okay, and will have a capability to even cut a metal sheet. Okay, so that's the capability of lasers and what makes the lasers produce. Okay, how, in what way the lasers are different from the normal light, we'll have a discussion. Okay, prior to this lasers, we have actually acronym called MASER, MASER. Okay, and MASER is microwave amplification by stimulated emission of radiation. Okay, and they have done by using ammonia gas and the microwave radiation. Okay, and further in 1960, ruby laser has been developed. Okay, by Maiman, and they were successful in producing the laser light. Okay, so this one, ruby is a kind of a crystal. Okay, and from the ruby crystal, the laser light has been produced, and has got many applications as well. Okay, so that's the brief history. Okay, I'm not going much into details. As I said, we focus mainly on the ones which are required for your examination, and some topics where they are definitely coming up in your exam. Okay, so those things we will be discussing. It's not like each and every point may be discussed. I may not be. Okay, it's not practically possible. Okay, so the major thing is here that what are the important things from this topics we will be discussing. Okay, without wasting time, let's go ahead with the application first. Okay, so first one, if you can note down what we are discussing instead of just listening to, you can keep a note on it. Yeah, applications of lasers. Applications has got lasers in many areas, as I said, in medicine. Okay, ruby laser particularly, it can be used. It can be used as in medicine. Okay, so also in ophthalmology. Already I got a comment here that the voice is not clear. Hello, how can I help them? If my voice is not clear, see, I'm what can I how can I improve? How can I improve the voice? Okay, Bluetooth, everything is connected, correct? Okay, fine, but I don't know. Okay, so the next one is the ruby laser can be useful in terms of ophthalmology. In ophthalmology, okay, that means eye operations. Okay, ruby laser is very much used, and it's also in the dermatology. Okay, dermatology, that's a pigmentation removal. Okay, the lasers can be used and safe, and why these lasers can be used in pigmentations are because they have the very accurate um, spotting. Okay, so they'll be actually focused to a desired place only. So that's the beauty of lasers. Okay, and they have the capability to remove tiny structures. Okay, small structures, which are on the face, and to remove those. Okay, the lasers are very much useful, and without damaging to the surrounding tissue. If the tissues are being damaged, okay, and again one complication. So instead, lasers are quite useful, and they are not having a side effect. Okay, and then in general, we have many uses. For example, if I have here for the plastic surgery, cardiovascular surgeries. Okay, we have here neurosurgeries, and so also in urology, gynecology. Why I am telling all these things is because see, just have a look. Sometimes there will be a question that how lasers can be used in medicine. Okay, so this question will be handy. Okay, and the next One is the cardiovascular surgeries, and then we have neurosurgery. Okay, then we have here the oncology. Okay, and removal, that is removal of kidney stones. The cancer diagnosis. Okay, and further we have laser angioplasty, and artery blocks and anything like that will also be get cleared by using lasers. Okay, lasers has got wide applications even in medicines. Okay, and so also in industry. In industry, we have many uses in the form of welding, yeah, welding, drilling, cutting, okay, trimming, okay, to the precision. Okay, so that's what the accuracy these lasers are used for. Okay, and the lasers can be also be used in microelectronics, in electronic boards, circuits. Okay, where suppose you wanted to remove some certain devices, okay, from the electronic circuit boards, and the other the damaged ones can be removed by using the lasers without disturbing the other equipment, okay, other parts, okay, and this can be achieved by the lasers, okay, and further we have here the astronomy in astronomy. Astronomy radar systems to emit the radiation, and that will be useful to study in astronomy, and so also in ecology. In ecology, that is finding out the air pollution. Okay, so number of particles, for instance, how many dust particles. Dust particles are present for area or something that can be found out by using laser. Okay, and in computer science, of course, in computers, in DVD writing and all, the lasers can be very much useful. And further, we have in the helium neon lasers. Okay, the helium neon lasers, okay, that can be used in many places. For instance, in olden times, people used to helium neon lasers. They used for the checkouts at the checkouts in supermarket. Okay, so in US, somewhere around 20s, the helium neon lasers has been checkouts. Okay, it's a bit complicated, but here nowadays the semiconductor laser has been used in checkouts in the supermarket. Okay, these are the applications, wide applications, because there are wide applications in various fields. It's our duty to understand uh, what the laser is, okay, what are the properties of lasers, okay. We will start with what is this laser, okay. I'll tell you by drawing some diagrams. Okay, right. We have actually the atoms, okay. We have atoms. You all know that the electrons are all being present, yeah, and the nucleus is at the center on the other object. Yeah. You know that this is how the electrons are all being placed, and the electrons are all moving around. Yeah. Okay. So when if that is the case, okay, in some substances, okay, we are talking about, and if that is the case, then the light is being put, ordinary light, okay, and the ordinary light has been incident on this substance, for instance, like this, okay, ordinary light has been incident on this substance. Then what happens is, as a result, the light is okay, the light is absorbed. The light is absorbed by the electrons, and the electrons will absorb the radiation. Okay. Once the absorption has been done, then what happens is, as a result, then there is an energy. Okay, there will be some kind of energy accumulation. Okay, so the energy is gained by the, let us say, electron number one has absorbed the energy, light energy. Okay, and then as a result, what happens? It will gain more energy. Okay, it will gain more energy, and what happens is, as a result, once it gains more energy, then what happens? It goes from one state to the another state. Like, okay, it goes from one state to the another state. Okay, and also some other electrons, they may go to the other state. So state one, state two, like that they may be going. So what happens is if they first rise up, they go to the upper levels. Okay, once they go to the upper levels, they come back to the lower levels. Okay, and the difference of energy gives up in the form of radiation. Once again, the electrons first of all gain energy from the incident light. Okay, and they once they gain energy, they will go to the upper level. Okay, the upper energy state, and they come back to the lower energy state, and the difference of energy goes off in the form of radiation. Okay, some textbooks will be giving you as atoms. Okay, they will be, because there should not be any kind of confusion. Okay, so here what we do is here, see, we talk about a substance. We talk about a substance, and we talk about all the atoms are being present. Light has been falling onto these substances. Then, as a result, absorption takes place, and then they will be going to the upper energy levels. And they come to the lower energy levels, and the difference of energy gives off the form of radiation. That is in the case of one atom, for example. Okay, and so is the case with the other atom, because there are numerous atoms present in the substance. When the radiation is continuously falling onto that substance, then absorption takes place, and these atoms will gain energy, and they go to the upper energy levels, and they come back to the lower energy levels, and thereby the difference of energy gives off in the form of radiation. Maybe it is giving one speck of light, for instance, let us say. Then, like that, there are so many atoms being present, and so many atoms get excited, so many atoms goes to the upper energy levels, so many atoms come back to the lower energy levels, and the difference of energy arises, and the difference of energy gives us form of radiation. Radiation 1, radiation 2, radiation 3, 4, and consolidated, all those things will give you a laser light. This is what the actually laser is. Okay, so if you have any issues, then I'll tell you on this. See, what happens is, once again, we have here a substance. A substance, light falls onto that substance. Then, as a result of that, okay, then as a result of this, then there will be an absorption. When the light falls onto this, okay, there is an absorption. Someone is asking what topic I'm talking about. I'm talking about lasers. Okay, for the latecomers, I'm talking about lasers. Okay, and then what happens is that the metal will have many atoms. Okay, when the light rays falls onto that substances, then as a result, what happens is that the atoms will gain energy. Once they gain energy, they goes to the lower level to the upper energy level. Okay, it's not necessary that all the atoms go to the only one state. No, not necessary. So it depends on the energy, how much the energy they gain. So from the lower energy state, let us say E1, you talk about. Okay, I will draw the diagram and show you. So they may be going from the state E1 to E2, maybe E3, maybe E4. Okay, so let us say I'll draw the diagram and I will show it to you how it will be. Okay, see, for instance, like various combinations are possible. Okay, state E1 we have here, E2 here, we have E3, we have E4. Okay, like this. Okay, we have E1, E2, E3, and E4. From the lower stage, they may go to the E2. They may go to the E3. They may go to the E4, something like that. Okay. So it's what happens is that it is instant. Okay, when the light falls, immediately it will happen. This absorption takes place, and again it goes to the upper energy levels. They come back to lower energy levels, and the difference of energy comes out in the form of radiation. All these things will take in a fraction of light, fraction of seconds. Okay. You just turn on the light and it starts working. Okay, so that's how it's happening. Okay, the lasers. Okay, now slowly we move on to the characteristics. That's about lasers, and we talk about the characteristics. Characteristics generally in the exam they'll be asking about the write the characteristics of lasers. What is laser? Okay, write the history of laser briefly, and also write about the characteristics. Maybe they may give in the form of short questions. Okay, so first of all, to begin with the characteristics we have, one of them is directionality, high directionality. Okay, high directionality, high direction, high directionality. Okay, characteristics. Many characteristics are there. One of them is high directionality. Okay, why? What makes this high directionality? That the lasers can be actually going to a particular direction. Okay, without much of deviation. Okay, rather. So, how in simple words is, I'll tell you, if the radiation going 1 meter, it is traveling, for instance, laser beam, then you'll have only 1 mm deviation per meter. See, this is what. Okay, 1 mm per 1 meter. 1 meter distance has been traveled from laser. There will be a deviation of just 1 mm, which is very much negligible. Okay, a small deviation. So you can understand that it's pinpointed. It all goes in a particular direction. Okay, and not much of deviation. Okay, and whereas same is the case with the other thing. For example, if you compare how the light will be passed, okay, and an ordinary rays, for instance, is a laser rays, okay, and the ordinary rays will have here 1 meter. When you're talking about here, there will be a deviation of absolutely 1. Okay, and that's the difference here. Lasers will have 1 mm deviation per 1 meter, whereas the ordinary rays will have a 1 meter and 1 meter deviation. That means the light goes in all directions in the ordinary light, whereas this lasers will be going in one particular direction because of the highly intensified beam. Okay, so that's about the lasers characteristics. Okay. Further, we have here the number 2 is intensity. Okay, as I said, the lasers will have the intensity and the intensity to even drill the holes in iron. Okay, and they can have the capacity to cut the metal sheet. Okay, and so on. There are so many applications. Okay, we are already. So here the intensity. Intensity is another feature, another characteristic. See here characteristics and the applications are different from each other. Hello, most of the students always when we ask for the characteristics, most of the students will be mistaken and they are writing application, which is wrong. I'm telling very clearly, characteristics or features is same. Characteristics or features is same, but applications are different. Okay, applications when they ask for applications, and you are supposed to write the applications only. Okay, and when we ask for the features or characteristics, the one what I'm talking about, like high directionality, high intensity, high monochromaticity, and high coherence. Okay, so these are the features we have to describe. And okay, let's go into the details. Next one is, as I said, intensity. Intensity is actually, as I said, like lasers will have very high intensity, very high intensity. And 1 milliwatt laser, when we talk about 1 milliwatt of laser is brighter than sun. Okay, so that is the feature of the intensity. Okay, intensity of lasers are so brighter that 1 milliwatt laser is brighter than sun due to coherence and direction. High coherence. Coherence, I'll come back to that. Okay, I'll tell you what is coherence. Okay, so what you have to understand first, just now we talked about high directionality, very high directionality, and number 2 is high intensity. Okay, as got high, very much high intensity, and further we have here the monochromatic. Yeah, monochromaticity. When we talk about monochromaticity, by this time you'd have understood what I'm talking about, isn't it? Monochromaticity is something like a single wavelength. Okay, it's a single wavelength. When we are talking about the radiation, instead of having many wavelengths, like ordinary light will have many wavelengths, laser will have only a single wavelength. Okay, so that is the one we are talking about. Oh, okay, so the third one is said to be here what? Monochromaticity. 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 And the ordinary light, usually what happens is it spreads over a wide range of frequencies, and the bandwidth of laser beam is 1 kilocycle. See, 1 kilocycle per second. Okay, whereas the ruby laser width has 5 times 10 power of minus 4 angstroms. Okay, the ruby laser line width is 5 times 10 power of 5 times 10 power of minus 4 angstrom. Okay, just a comparison. Okay, once again, the bandwidth of laser beam is approximately 1 kilocycle per second, whereas the ruby laser line width is 5 times 10 power of minus 4 angstroms. Okay, why this is being given is to have an idea of how much the transmission is taking place with the monochromatic rays of laser. Okay. Oh, yeah. Coming to the next point. So what we have discussed now, high directionality, one of them. Next one is intensity. Next one is monochromaticity. And the next one is talking about coherence. Yeah, coherence. Suppose if I say coherence and just go to the next point, it's not fair. But you have to know what is coherence. I'll tell you. Coherence is actually the degree of coherence of laser beam is very high than the other sources. Coherence, I will tell you what is coherence. See, suppose we have the substance here, I'll draw the diagram. Yeah, we have here the substance, okay, and we have here atoms, okay, for instance, those I have drawn them as atoms, okay. We have the substance, and some atoms are being present in that material, for instance. When the light falls onto this substance, then there are from the different places from which the light emits. Okay, from the different places. This is one place. This is one place. I'll tell you. And this one. See the aroma. Okay, so the light is coming up from the different place. When the light comes in the different places, okay, and let us say from one wave is something like this, okay, and the other wave is something like this, okay, and the third wave is also like this. So what do you observe? If you see the diagram like that, so wave one is said to be having crest trough, crest trough. Wave 2 is also having crest trough, crest trough. Wave 3 is also having crest trough, crest trough. So all these waves are emanating from different places from the substance, different places within the substance. Mind this, okay? Once again, different places within the substance, the waves are coming out. That is laser beam, okay? And here, the first wave starts with the crest trough, crest trough, crest trough, like that, okay? Second wave also starts with crest trough, okay? And further, the third wave also starts with crescent. That means these three waves, for example, I am talking about three waves are in phase with each other. So if they combine, then as a result, there will be a constructive interference. Okay. Once this combine, so like this, there are many ways. What if the radiation is coming out and the wave is coming out in a different manner? Okay. See, for instance, like this one. This one I'm talking about. Okay. A different style means a trough crest. Okay. Trough crest. Again, trough crest. Like that. So it starts with the trough. Okay. And this is trough crest. Trough crest. So the previous three waves are having crest trough and this one is having trough crest. So this is a different. Okay. A different manner. So let us say this kind of waves also come. Okay. But they are very little. Okay, they are very little. Then what happens if that type of waves comes and combines? Then it leads to a destructive interference. Okay, destructive interference, rather the interference is destructive interference, and then the wave cannot be transmitted further. Okay, so that will happen, but it's very small in quantity. Okay, so that is the wave is not in phase. Remember, not in phase. Okay. So other three waves, what I have drawn here, shown to you, are said to be in phase with each other, whereas this one is not in. Okay, so that is what is said. We suppose if they are all in phase with each other, and then we say that they are coherent. Okay, coherent beam, or rather, see here, they are all coming from one particular direction. They are going in a one particular generated and being going in a one particular direction. Okay, so the laser source have identical in phase and direction. That's what I'm talking about. Phase and direction in propagation. While they are propagating, they'll have phase and particular direction. And it actually, they'll have a focus of 0.7 mm thickness. Okay? So these are the things about the features of characteristics of lasers. Okay, like this, we'll slowly move on to the topics. Like for instance, we have spontaneous emission. Okay, what are said to be the spontaneous emissions? What are said to be the population inverse? Types of emissions, first of all, we will discuss about types. Okay, so here lasers will have different types of emissions. Okay, so questions may be asked, and generally they will be asking you to discuss about the various types of emissions. What is laser? Explain about various types of lasers. One question maybe. Another question maybe something like what is a laser, and explain the characteristics of lasers maybe asked. Okay, and a question may be asked like what is laser, and explain about spontaneous and stimulated emissions. Or a question may be asked like distinguish between spontaneous and stimulated emissions. A professor may give a different type of questions. Okay, but the content will remain same. So all I is talking about is spontaneous and stimulated emissions. There are different types of emissions. There's a slight difference between spontaneous emission and the stimulated emission. Okay, so we'll discuss about the spontaneous and stimulated emissions. Okay, okay. If I will draw some diagrams to make it understand. Okay, so if an electron is an excited energy, for instance, okay, if an electron is in an excited energy state, it must be, it must come back, it must decay to the lower energy level. Okay, as I said, see what happens here. If we have here, we have here different states. Okay, we have here different states, different states. Then we name it as state E1, E2, and E3. Okay, state E1, E2, and E3. They are the different states. Okay, and we have here the atoms, or we can say the electrons. They are all going to the upper energy levels. Okay, they're all going to the upper energy levels like that. Once they go to the upper energy levels, they'll come back. They must come back to the lower energy level. Okay, they must come back to the lower energy. So what happens is like if an electron, if an electron is in an excited energy state, it must decay to the lower energy level. Okay, giving off a photon of energy. What I said, we have here lower energy state and we have upper energy state. Okay, light rays falls onto these substances, then absorption takes place onto these atoms, and they goes to the upper energy levels, and they come back to the lower energy levels, and thereby the difference of energy goes off in the form of a photon. That happens with the one electron, and another electron also get excited at the same time. Okay, it get excited if it if the electron has got more energy, then it may go to the upper energy level. Okay, maybe like from the state E1 to the E2 or maybe E3, okay, or E4. Okay, then it may come to the E1 via E3, E2, and E1. Suppose E1 to E4, it has excited and gone to the third state. Then from E4 to E3 may come, and E3 to E2, and E2 to E1 like that, or maybe directly it may come. So there are various chances. It's not only just one electron goes from the lower energy level to the upper energy level. There are several electrons. Please understand that there are several electrons. They're all goes light falls onto these substances. More absorption takes place, goes up, and then again they get excited and they can come back, and again light falls. This is a continuous process. Like light rays falls, and then the absorption takes place, it goes up, and again it goes up, and again it comes back. So like this is a cyclic process, like continuously it takes place like that, until and unless you continuously give the light. And the question is here that how long does this continue? Okay, so as long as the electrons get bigger, okay, they exhausted, they get exhausted at one stage. See, for instance, this continual process, it's not like it will be useful for some several years. Right? No, it has got some. So what will happen is it reaches to a certain peak level. Okay, so the further this process stops at one stage. Okay, so that is the one. Okay, anyways, talking about this spontaneous and simulated radiation. So if the okay, so if the event is called actually the photon is emitted in a random direction. Suppose if the radiations are going from lower levels to the upper levels, okay, and the emissions are all giving off in a random direction. Okay, for instance, they are all in random direction and random phase. Then this type of emission is called spontaneous emission. Once again, then what did I say? I said that here the electrons they gain energy, okay, and they goes to the upper energy levels, and they come back to lower energy levels, and the difference of energy gives off in the form of radiation, and then the emission of radiation will come out, okay, the photons will be ejected, and here the photons once they ejected they go in a random direction and random phase, then we call it as the spontaneous emission. Okay, please understand that is what is said to be here, the spontaneous emission. Okay, and the average time it takes is that the electron decay is said to be the time constant. Okay, that's what we call it as time constant for the spontaneous emission. Okay, and further, see, on the other hand, this is what is said to be here, the spontaneous emission. Further, we have here the other one is said to be here, the stimulated emission. What is stimulated emission? Let's have a discussion. See. Suppose if the electron gains energy, okay, and it goes from the energy state E1 to E2, and the decay path is said to be here E2 to E1. So it goes from the E2, it goes from the E1 to E2, and again it comes back to E1, and then the photon happens to pass those energy approximately E2 minus E1. There's a probability that the passing photon will cause the electron to decay in such a manner that a photon is emitted exactly the same wavelength in same direction. Same wavelength in same direction and exactly same phase. Okay. And suppose if that the emission takes place, okay, in the same direction and in the same phase. So please try to understand in simple words. Spontaneous emission is the one where the emission takes place in random, okay, random direction and random phase. Whereas if the same emission takes place in the same direction and same phase, that's what is said to be simulated emission. Okay, simulated emission. Okay, so that's what the spontaneous and stimulated emissions are all about. Okay, yeah. So very quickly, we will have a comparison between the spontaneous emission and the stimulated emission. For instance, the spontaneous we are talking about. Excited states are metastable and most decay first. You have to know what is metastable. Okay, the metastable is, I'll tell you. We have here, in detail I'll tell you, but roughly you have to know is it. So the we have here E1 and E2 states. Okay, E1 and E2 states, and in between state rather intermediate state. Okay, the diagram I'll show you. Okay, We have here E1, we have E2. In between state is said to be the metastable state. Okay, in between state is intermediate state. Sometimes some textbooks they will be mentioning as intermediate state. Okay, so in the examination, let us say an intermediate state. Don't think that that's an out of syllabus or something. So they are talking about metastable state. Okay, metastable state or intermediate state is one and the same. Okay, then let's see here what happens. Once the radiation has been when radiation means light falls onto the substance, then the electrons will get excited. They goes to the upper levels, yeah, and they goes to the lower. They goes to the upper levels, and they come to the lower levels via in between state. Okay, so I'll draw the diagram to show you that the electrons in the ground state, okay, they goes to the upper energy levels called E2. So they will be going to the upper energy levels. Okay, once they go to the upper energy levels, within a time span of 10 power of minus 8, okay, they come back to the lower energy level. Instead, what happens is here that they will be all coming to E2. Okay, from E2 to E1 they will come and see the diagram. Okay, try to understand. From E1 they goes to the E2. Okay, from E2 they reach at the other one called metastable state. That is metastable state. Okay, metastable. I'll write down metastable state. What happens is here all the other electrons they will wait for a while. Okay, this is what you have to understand. Okay, see, they will wait, and that means it's a 10 power of minus 7 seconds. Okay, so here from E1 to E2 they will get excited. Okay, and they goes to the upper energy levels, and they come back to the lower energy level called E1 via a state in between called metastable state. It's called metastable state. Okay, once again, the electrons they get excited. They goes from the level E1 to E2, and they come back from E2 to E1 via via an intermediate state called metastable state. Okay, here all the electrons will wait till the rest of the electrons comes and they jump. Okay, here together. Once they jump together, all we get is an output which is more stronger with more intensity. Okay, so that's what you have to understand like that. This metastable state. Okay, so that's why I use the term. See, I had to explain it to why I am using here metastable state. Suppose if I say just that the excited states or metastable state and most decay, if I say that, you don't understand immediately what we are talking. So what is this? Excited states or metastable states, and they must decay. Okay, they must decay. Right. Next one is in case of stimulated lasers, they are faster emission down than spontaneous. Okay, they are much faster when we talk about the stimulated lasers. Okay, and coming back to the spontaneous lasers, the excited states have lifetimes ranging from milliseconds. As I said, like 10 power of minus 3 seconds, isn't it? So from the ground level to the upper energy levels, and they again come back to the lower energy levels within a time span of 10 power of minus 8 seconds. But here, see, excited states have lifetimes ranging from milliseconds. Okay, it's a 10 power of minus 6 seconds to have 10 power of minus 9 seconds. Okay, and further, see, excited photons and in case of stimulated photons, emitted photons are indistinguishable. See, the word indistinguishable means by this time you would have understood that when you will be knowing more when you study about anything about the statistical. Okay, so these atoms are indistinguishable. When this term called indistinguishable are used, okay, usually in molecules we use the term in statistical mechanics. Indistinguishable means all the atoms, let us say all the electrons we talk about, for instance, they're all been grouped together. Okay, when they are grouped together, then it's difficult to identify. They are like a flow. okay, like a beam. So that's why we call it as indistinguishable. Why I am talking about indistinguishable is that means in stimulated emission, we get the radiation in the form of indistinguishable particles. That means it comes out in the form of radiation, a beam. Okay, it's not like a speck of light. No, it's not a speck of light. It is a kind of a beam. Okay, continuous beam. Okay, that's how the radiation will be coming out. Okay, and the excited photon here in case of stimulated emission, the excited photon interacts with photon, another photon. So this one is a very important point you must remember. Okay, the excited photons interacts with another. Okay, once they see here, the photon is getting excited. Okay, it interacts with the other photon. Okay, so that's what it happens. Okay, and the stimulated photon have same frequency and direction as I said, like they are in phase and they combine with each other and they have a constructive interference and they'll be moving forward. Well, okay, so it's not much of opposition. Okay, and that's how they are like phase and they are having the electromagnetic polarization as well. Okay, whereas in case of spontaneous emissions, emissions has got excited electrons or molecules to be there and it decays to an available lower energy level and in the process gives off a photon and does not involve in the interaction of other photons. This is what the difference is. Please try to understand. Once again, the photon interacts with other photon in stimulated emission. Photon does not interact with the other photon in spontaneous emission. Why? The question is why? It happens because the radiation goes off randomly in random direction, okay, in random phase. In case of spontaneous emission, okay, in case of stimulated emission, they all goes in a proper direction and proper phase, and that's why they're all interact with the other photon. Okay, that's what is the thing is, and this major difference. This is what just think in your mind that oh, what is the difference between spontaneous emission and stimulated emission? Spontaneous emission, as I said, that radiation will come. So both are said to be having same principle, but just a little bit of difference. Okay, the radiation comes here. Okay, and they goes in a random direction, random direction, and random phase means you can understand that whenever I say that it goes off in the random direction and in a random phase, you can understand that it may not uh, radiate to a longer distance random direction. It goes off in random direction. It should not. It should go in a particular direction. Okay, that's what the difference, major difference is between the spontaneous emission and stimulated emission. In stimulated emission is the one where it goes, the radiation goes in a beam. Okay, in a continuous manner in a beam, and it can go to a longer distance. Okay, that's what one thing. Another thing is that the photons will be interacting more with the other photons in case of the the stimulated emission. Okay, that's what the laser name what they have named it as light amplification by stimulated emission of radiation. Okay, that's what the meaning is. Okay, and these are the differences between the spontaneous emission and the stimulated emission. Okay, yeah. Further, we will move on to the working principles. We can have an optical pumping and all many things are there. Okay, uh, we can have something like the we have the production, of course. Production is also there, but I don't want to go to the production before telling anything about the optical pumping. Also, you have to know. Okay, once we know about optical pumping, then we will be know about the production. Okay. Okay. So we'll have some basics now, and one of them is the population inversion. Okay, the population inversion we talked about. This all usually comes under short questions. Okay, population inversion. Inversion is explain about the population inversion and optical pumping in laser. Maybe a question, maybe coming for short questions. That's why I'm telling you, do not let loose any question from the laser. Okay, it's one of the easiest. Population inversion. Okay, so what is this population inversion? The name itself says population inversion. Something like some reverse is taking place. Something is reversed. Here, what is happening is here that when the atom, when the electrons are being taken, okay, they are taking the energy and they are going from the lower energy level to the upper energy level, right? So everyone is familiar now. Okay, the light radiation falls. First, light falls, okay, onto the substance. Then a suitable substance. It's not like all the substances from which the laser light comes. I didn't tell that. Okay, once again, it's not like all the substances from which the laser comes. No, it is not. There are some suitable substances only. From there only you will get the laser radiation. Okay, and here what I'm talking about. Okay, when the light rays falls onto these substances, then as a result, the electrons will get excited. They get excited. Let us say electron number 1 get excited. It goes to the upper level. Okay, don't think that I'm talking about again and again same. No, this is a bit different. How I'll do. So first electron will get excited to the upper level. Okay, and here what happens here? Again, the second electron also goes. They get excited and goes to the third electron also gets excited, goes to the upper level. Like that, there are so many electrons from the lower energy level to the upper level. At one stage, you see what happens here, that all electrons will not be staying for a fraction of a second, that they will not be anything in the ground state. So what happens, they all get excited for a fraction of a second, they goes to the upper energy levels. So initially, they are all full in the ground state. Once the light falls and then the absorption takes place, immediately they will all be vacating the lower energy state and they all go to the upper energy state. Okay. And then again they will be coming back to lower energy state. Okay, there's a cyclic process. Just a pause for a second here. What happens is here that light rays falls onto this electrons. Electrons get excited. So many number of electrons get excited and they go to the upper energy levels and the lower energy state will become completely empty and the upper energy level will become full. Initially, how it was? Initially, the lower energy level was full and the upper energy level was empty. And then once the light falls onto the substance, then absorption takes place. Then all the electrons will be going from the lower energy levels to the upper energy levels. Then the lower energy level will become completely empty and the upper energy level will become completely full with the electrons. Okay. So this is said to be the population. And again, what happens here? They come back from the, let us say, they goes from the E4 level to the E3 level. They will come back. Maybe sometimes they make up, jump from the E4 to the E1, or maybe they will go to the E4 to E3, E3 to E2, and E2 to E1, or maybe E4 directly to E2, or E4 to E1. Like this, there are so many combinations. You can understand that it's said to be here. Suppose if I'm talking about E1, E2, E3, and E4. That means what I'm talking about here is a 4-level energy I am talking about. Okay, it's a 4, let us say, in some textbooks they will be mentioning here, 4-level energy. What is this 4-level energy? Is this one. Okay, so we have here energy level number 1, energy level 2, energy level 3, energy level 4 we have here. Okay, so the electrons will have much energy in such a way that they goes from the lower state onto the first state, second state, third state, or even fourth. Okay, if that production of lasers are in such a way that they have the capability to go that electrons to go to the lower levels to the highest fourth level, and that's what is going to be a 4 energy level laser. Okay, that's what the 4 energy level. Okay, fourth level energy level laser. Okay. And see, the population inversion, that's not what I'm talking about. No. So we are talking about what? Lower energy level to the upper energy level. I'm talking about only 2 states, okay? E1 and E2. Between E1 and E2, what happens here? The radiations, the electrons will goes to the lower level to upper level. Lower level will become completely empty and the upper level will become full. Okay, and the upper level, after some time, upper level will all become completely empty and the lower level that's what the cyclic process takes place. Okay. And it is not restricted to only first and second levels. Please try to understand once again that the radiation, this population inversion will not take place only between first and second. I think that. Okay. Once again, the population inversion may take place between state E1 to E2, E2 to E3, E3 to E4. Either different places where the population inversion is said to be achieved. Once again, population inversion is said to be achieved in various states, maybe between E1 to E2, E2 to E3, E3 to E4, or like anything like E4 to E3 or E4 to E2 or something. So the population inversion is said to be achieved between various states. Okay, so this is what the population inversion is about. Okay, and yeah, of course, we can talk about the basics, something like short questions, like generally they'll be asking you about the coherence or something like that. They will be asking in the exam to write a brief note, for instance, okay, on the coherence. Okay, coherence, as I said, like the emission is taking place from the different places within the substance. A substance we have here, one substance we have. From one place, you'll get radiation. Another place, you'll get. From one place, you're getting. From different place, you're getting the radiation. Okay, first, this is the basic concept. Different places from which the radiation is coming out. And of course, while producing lasers, we have here the rays that will be coming to one place. Okay, that's what anyway that will be done. So here what happens is that the radiation which is coming from the source one, we call it as source one. Okay, we have a trough like that wave is coming out. Okay, and the second phase from which we have a crest of. So here first wave and second wave are said to be in phase with each other. Suppose if they are coming from the trough and the crest, then they both are 180 degrees out of phase. That is destructive interference. Okay, this is said to be destructive interference. So the waves goes from the starts from a crest trough, and another wave starts from crest trough, and both are happen to meet. Then both are said to be in phase with each other. Both are said to be in phase with each other. Then it transmits with a much higher intensity. Okay, like that. There are so many places from which this type of waves comes out. Okay, and thereby it helps to propagate. Okay, with ease, and that's why the waves are said to be here coherent. Okay, they are coherent. Okay, that's the concept. We go into details. Okay, like coherence is one of the they have unique properties of laser, like I said. This is the special property the lasers have. Okay, and this is has been erased from the stimulated emission, as I have discussed just now about the stimulated and spontaneous emission. Okay, it happens generally in stimulated emission process, which provides the amplification. The why term called, what is the term called amplification? What does it mean to you? Okay, amplification is something like if you take a signal and increase the strength of the signal, and the signal is said to be amplified. Okay, so increasing the strength of the signal is said to be amplification. So in the case here, like we are amplifying the, or rather the increasing the intensity of light, and that's why we call term called amplification. Okay, and further see, uh, since a common stimulus triggers the emission events which provides the amplified light, then the emitted photons are in step to have definite phase to each other. They will have a different phase. That's what I'm telling you, different phase. Then only they'll lead to a constructive interference. Otherwise, a destructive interference. It doesn't mean that the destructive interference does not take place, but a very small in number. Let us say 1 in 1,000, something like that. Okay, one is something which is not having the phase, and all other things are having the phase. Okay, so that's how the radiation is going on. Okay, and this coherence is distributed in terms of temporal coherence and spatial coherence. Temporal in terms of time, okay, in terms of time, the coherence is taking place, and in terms of space. Okay, that's why they are called temporal coherence and the spatial coherence. They'll be calling as temporal and spatial coherence. And the ordinary light is not coherent. Okay, the ordinary light is not coherent because it comes from the individual atoms which emit on the time scales. Okay, so that's what the thing is. Already I said that it's not having a single wavelength but various gradations. Okay, and they all go in the different directions. Okay, and that is different from the laser light. And there's a degree of coherence in sources like that. For instance, we talk about green line, something like that. Okay, and they approach that of a laser. To see coherence does not approach that of a laser. See, there is some issues. For instance, some of the atoms may not be cooperating to have the coherence. Some atoms, that's what I'm telling you, because of various reasons and because of the impurities or maybe in the substance present. Okay, and the light rays, all the atoms, it's not necessary that all the electrons must get excited. They won't. But majority of the electrons get excited. They goes to the upper levels. Okay, and further some of the electrons they may go in a particular direction. Some may not. Some go in a random direction. Okay, some direction. So some direction, some of the electrons may go. As a result, then we usually ignore. We try to direct them to the beam. Okay, and some of them they may go. Okay, so that's what the thing is about the coherence. Okay. Okay. Further, we have here a ruby laser. So today, what we do is we talk about the ruby laser because ruby laser is the one where how we produce the light. Okay, how we produce the light uh, the by arrangement and how I'll tell you. This is actually the experiment. Okay, it's an experiment to produce the light. Okay, in the exam they may be asked like how about the examination, how they did. Straight away they may be asked like explain about the ruby laser functionality by drawing the four-level diagram. That's what the question may be asked. Okay, once again. In the examination, they may be asking, describe about the UV laser with the four-level diagram, energy level diagram. They will be asking like this. So what you have to do is to first draw the diagram for the experiment, and you have to explain what parts it has, and then how does it function, description, okay, and the functionality, working principle you have to write, and then the output, okay, and then the output, okay, and for uh, energy level diagram. Energy level diagrams, as I said, like here it goes from the lower level to the one level, okay, two levels, three levels, and four levels. This particular ruby laser can produce the electrons and goes from the lower energy levels to the four energy levels, okay, and that's why it's a four-level laser, okay, four-level laser, okay, right. So let's start with the ruby crystal, okay. Ruby crystal. Ruby is actually, first of all, to begin with, the notes I'll send you. Hello, the notes. Don't worry about the notes. I will give you the notes. But here you have to understand the concept of how it functions. Okay, I'll show you the diagram. How does it function? Okay. First of all, to begin with, the ruby laser. Ruby is a crystal. Ruby is Al2O3. Okay, is a crystal. Okay, and here Al is replaced by Cr3 ions. Okay, Al is replaced by Cr3 ions, and then a high intensity. Here, what we use is helical flash tube. Okay, helical flash tube. Helical is like a circular tube, like a circular tube. Okay, usually you find them in outside. You find them as evening advertisement. Okay, it's round, folded, light. Okay, that kind of arrangement. Okay, so we have here a kind of a test tube like, okay, a glass tube rather. We don't say test tube, but it's a glass tube. It's a glass tube. Okay, it's been surrounded by helical flash tube, usually called as xenon flash tube. Okay, and that is the actually source of it. See how we are producing. Please try to understand that we are using light, and that light is producing laser. Okay, so try to understand. We are using here a light, okay, high intensity light, no, normal light. Okay, we are using, and then from there we are producing the laser light. How means what happens is we are using a ruby crystal. Ruby crystal has been placed in a glass tube. Okay, and then it's been surrounded by helical flash tube. Okay, and the helical flash tube has been connected to a power source. Has been connected to the power source, and light is turned on. Then what happens when the light falls onto this ruby crystal? Then what happens? Light rays falls onto this ruby crystal. Ruby crystal will have atoms. As I said, like why they have chosen this rail to play? Why they have chosen this ruby only? Because it has the capability to produce the lasers. They have tried and tested. Okay, so they have people have worked on it and they have tried and tested with the various substances, and they found ruby is the best source. Okay, is one of the good sources of producing the laser. Already I said that not all the substances from which you will get the lasers. There are some only specific substances from there only you will be getting the laser. Okay, so here I'll show you the diagram, and then you'll have a feel of what I'm talking about. See, this was the diagram. Okay, so okay, see, that's the glass tube. Okay, that's the glass tube that's been surrounded. Okay, glass tube. I'll show it close to you. See, that's the glass tube. It's been surrounded by helical flash tube. Okay, and the dark one, which is inside the glass tube, is said to be the helium. Not sorry, it's a ruby crystal. Okay, that's a ruby crystal, not the helium. Okay, we are not using helium here. Okay, and then it's been connected. See here, the helical flash tube. The helical flash tube. That's the helical flash tube. It's been connected to a power source. Okay, it's been connected to a power source, and see here, as a result, what happens to glass, isn't it? Because of glass and light has been surrounding, then as a result, being turned on, then as a result, it gets heated up. Okay, it gets heated up. At one stage, what happens is it gets very much heated. It may blast. Okay, so to avoid that, see, cooling of water. We are not directly pouring into it, but we are running some water through it. Okay, through a pipeline, the arrangement has been made in such a way that it runs water from one end to the other end. Then, as a result, the surroundings will get cooled. Okay, to avoid any kind of destruction. Okay, so that's been used like cooling water, running water rather. It goes from the one end and it comes out from the other end, and that's the source. Okay, and then see here, that's a helical flash tube. It's been connected. It's pretty clear. And the other thing you have to observe is there are two ends, okay, from which the radiation may come, isn't it? Then what happens is, though it's not shown in the figure here, that we have here one kind of fully reflecting surface, okay, and partially reflecting surface. We wanted actually the radiation to come from one single place to be safe. Okay, so here it should not come out in all over the place. It should not come the radiation from all over the place. No, it has to source from only one single entry. Then it will what it will have? It will have more. Right, first thing. Number two is safe. Okay, that's why what they have done is they have designed this ruby crystal in such a way that they are reflecting end. Okay, one part, all radiations, whatever goes, and it will get reflected to the other side, and from there the radiations come out. Okay, that's the output. It's a pretty clear and easy, much easier. Okay, so what we have very simple. Once again, I'll tell you, we have a glass tube. Okay, We have a lengthy glass tube. We have the ruby still has been placed inside the helical flash tube. There's a xenon flash tube. Okay, xenon flash tube is being connected to a high voltage source and to have high intensity of light. Okay, and the light rays falls on this ruby crystal. The ruby crystal will have two ends, and one end is highly reflecting side, other one is not. Okay, and that's how the arrangement is. Then, as a result of this, the rays falls onto this, and then absorption takes place. And then what happens? As the principle, as I said, once the light rays, falls from the helical flash tube, they fall onto this ruby crystal. And the ruby crystal will have atoms and the electrons will get absorbed. More electrons will be absorbed, and then they get excited. They goes to the upper levels, and they goes from the lower energy levels to the upper energy levels, like E1 to E2, 2 to E3, E2 to E3, and then E4. Okay, and then this particular one actually is a three-level laser. You can understand that we have here E1 to E2 to E3. It's a three-level laser. Okay. Okay, so remember that this is said to be the three-level laser. Okay, and the radiation will be coming off. The radiation will have, it will go to the as much as possible, like maximum three levels. Okay, so level E1 to E2 to E3, and then come back. Okay, and then the radiation follows. Okay, so that's how the construction is. Okay, as I said, like here, see how much of time it takes from E level to E2, E1 to E2. It's a 10 power of minus 8 seconds. Okay, so 10 power of minus 8 seconds. It goes from the lower level to the upper energy levels, and again come back to the lower energy levels within a time fraction of 10 times span of 10 power of minus 8 seconds. Okay, and whereas in metastable state, it takes longer. Okay, it takes longer, that is 10 power of minus 3. 10 power of minus 3 seconds. Okay, so what I said while I'm talking about the metastable state, I said that the electrons get excited from the lower energy levels to the upper energy levels, and they come to the lower energy levels via the intermediate state. Okay, intermediate state, and that intermediate state where they will stay longer. Longer in the sense, not much, but here 10 power of minus 3 seconds, and they come back here to the lower energy levels. So this, they will wait till all the other electrons comes, and they jump to it. Okay, and same is the case here. Here also same thing will take place. The metastable state is general concept, and that is happening also here. Okay, so here the electrons, what happens is, here the lower the electrons, they will be gaining energy from the helical flash tube. Okay, they gain the energy and they goes to the lower energy level to the upper energy levels. And if they have the more energy, they will be going from the E level to E2, E level E1 to E3. Okay, and again they will come back to the lower levels via metastable state. So each state we have here E1, E2, E3. So E1 to E2 in between one metastable state, E2 to E3 one metastable state, E2 to E3. So like that, there are several metastable states, and then that's how the transmission will take place. Okay, so that's quite easy. Okay, that's about the ruby crystal. So this one, see, all you have to do in the examination, like they'll be giving for essay type question absolutely, and all you have to do is, as I said, draw the diagram and describe the parts and how each part, how it will be functioning. Okay, and describe that how this laser functionality will take place, and then the output how it comes, the diagram and knowledge, and the level diagram I'll show you. So this you will understand what I'm talking about, right? Yeah.
Sir,
Okay, so that is this said to be the energy level diagram. So generally in the exam, they'll be asking you to draw the energy level diagram. Okay, of ruby laser. So this is what you are supposed to draw. Okay. Okay, that's quite simple. We have here E1 and we have here E2 and E3. Okay, that's about the energy lasers. And this particular ruby laser has got many applications. Always, it's a better to, even though they mention or not mention in your syllabus, it's always better to discuss about the applications. This particular ruby laser generally used for drilling holes. Initially, when I said that lasers, I said that lasers have the capacity to even drill the holes. Okay, so this particular ruby laser has got the capability to drill the holes, okay, to make the holes. Okay, and the other thing is that as high power systems, it can be used for high power systems for frequency doubling. Okay, for frequency doubling in UV spectrum. Okay, once again, high power systems can be used to for frequency doubling into UV spectrum. Okay, so that's one thing. Another one is it can be used in holographic camera, holographic camera, and can be used in medical laser. It can be used in laser. Okay, medical lasers. And for example, we have tattoos on the skin, so tattoos here, and then they will remove it by using the by using the by by using the ruby laser. Okay, the tattoos can be removed. Okay, and so also the cosmetic dermatology. These are all the practical applications. Okay, cosmetic dermatology, whether they ask for it or not, you mention that will be quite impressive. Okay, about the description, the diagram, the how the functionality, the working principle. Then if you write some applications and so also the energy diagram, 10 full marks will get. Okay, so this is it about the Ruby crystal. Okay, we have already studied about the population inversion, optical pumping and all. And then further we'll make a move towards the pivotal lasers. I don't think you have it in your syllabus. Okay, we'll have a look at some of the uh,
Sir, one question, sir. One
yeah,
doubt.
yeah, yeah.
So, so now we will have like three states, E1, E2, E3. So when
Yeah,
the light falls, so it gets excited and go to E3 state. And
yeah,
then when it returns back, it will come via E2
yeah.
and then maybe E2, E1. So can I call E2 as a metastable state, or
E-
there will be another state between E1 and E2? Or can
Even
I call
between
E2 as a metastable?
yeah, between E1 and E2, certainly E1 we have here, E2 we have another state. We name it, see here, sometimes in some textbooks, how they will be naming it as. Metastable state also, they will be giving state number, okay, like E1, E2, E3, for instance. The concept is here that you have to understand E1 to E2 gradation goes. Again, E2 to E1 directly won't come, but it comes from a middle state, that is intermediate state. It goes there and come back to the E1. Okay, so that's what it happens between E1 to E2 and E2 to E3 also. E2 to E3 also there will be an intermediate state or a metastable state. Okay,
Okay, sir. Yeah. Thank you, sir.
and further see as per the syllabus is concerned here, we'll have let me see what syllabus we have there. Notes I'll be sending you, okay, shortly after the class. Okay, just give me some time. Afterwards, I'll send you. But let me check about your syllabus is. Yeah. So you have here Ruby laser. Yeah, that's what I've covered. This till now. We have here NDYAG. We have GAF semiconductor laser. Okay. So you don't have helium neon laser. Okay. So we have semiconductor laser. Okay. I'll discuss about semiconductor laser right now. Okay. Right. Semiconductor laser. Okay. So in the exam, there are various means of asking the question. Okay. They'll be asked. Sometimes that's why I am asking about, why I am telling you sometimes about the how the questions will be asked, because sometimes some students, they prepare for the examination and they cannot understand the questions properly, and that's why I'm trying to break that one. Okay, and want to tell you that here a question may be asked in various ways, but must be in a position to answer. In the exam, there will be a question like, explain about any two solid state lasers. Immediately, a student may think that, oh, this is not in our syllabus or something. No, that is wrong. Okay, it's there in your syllabus and you have already studied. Okay, about to study this one thing at it. Solid state laser, ruby crystal, it comes under solid state laser. Now I'm talking about right now. I'm talking about a semiconductor laser. Semiconductor laser is also a solid state. So if you choose two, but not helium gas or something like that, you don't have it in syllabus, no. But you have to mention about NDYAG also you can discuss, okay, or ruby crystal or anything like semiconductor laser, anything like. Suppose if any question comes, usually they will mention by name, describe about the ruby crystal, describe about the NDYAG crystal, or discuss about the semiconductor laser that they will be asking. Okay. So anyway, semiconductor laser. A semiconductor can be used as a laser. Okay, semiconductor can be used as. In the previous case, we talked about the ruby will work as a laser. Okay, ruby is a laser. And what is the source in the? Can anyone tell the answer? What is the source in case of ruby crystal? What is the source of producing laser in ruby crystal? Can anyone answer? Just give an attempt. Make an attempt. Once again, what do you think the source in case of ruby crystal? What do you think the source in case of ruby crystal? How we are producing the lasers? What is the source? Can anyone tell? Just try.
Xenon lamp, something like that.
No, no. Yeah, neon lamp. You are talking about some helical xenon flash tube. You mean?
Yeah, I mean from there only the hits, right? So
Yeah, yeah, right. You are right. Right. So that is the source. Okay. So please try to understand that is the source. Okay. So what we are doing is we are actually using the light, the non-flash tube. We are using. Okay, that's the light we are using and producing the rays. Okay, that is the first one of the sources. Okay, one of the sources of producing the laser action. Okay, here we are doing what we are doing is here we are taking a semiconductor, not ordinary semiconductor. Okay, so ordinary semiconductors you know about, like for instance, by the time you would have studied, I don't know, you would have studied about. Whenever I say semiconductors, generally what comes to your mind is germanium silicon. Okay, germanium silicon is generally be used as semiconductor. But here in this case, we don't take germanium silicon, but we take GaAs, which is gallium arsenide. Gallium arsenide. Gallium arsenide is found to be very much useful in producing the laser. Okay, so that is the source. Okay, in this system, what is that? In this um, experiment, semiconductor laser, we take gallium arsenide. Okay, gallium arsenide as the substances. And then what is that principle? I'll tell you. We have very little time left. Okay, so what we do usually here in this case is like we actually dope more. Okay, doping. You know what is doping? Doping is adding of impurity to a pure semiconductor. Is said to be doping. Here, what we do is we dope in such a way that we have some thousands of substances getting entered into semiconductor. Once again, what we dope is we wanted the most of the foreign atoms to enter into the semiconductor, enter into the semiconductor. Okay, and then what happens here? If more number of, let us say, uh, we have here p-type semiconductors, we have n-type semiconductor, you all know. Okay, here in this case, for instance, we are talking about p-type. Okay, p-type, you know, the majority charge carriers are said to be holes, and n-type are said to be majority charge carriers or electrons here. Okay, and so what happens is if more number of charge carriers are being present, then we allow them to combine. The p-type semiconductor is connected to the positive of a battery, and n-type semiconductor is connected to the negative of the battery, and more number of charge carriers are made available. If more number of charge carriers are made available, okay, then what happens here? More number of absorptions take place. Okay, electron hole absorption. Okay, one electron and hole absorption. So we generate a process. Okay, we generate a process in such a way that one electron, one hole, one electron, one hole, one electron, one hole. Combination takes. What is the fun in doing so? Why we are doing it? I'll tell you. We have here, let us say, 100 atoms. We make it into 1,000 atoms, 1,000 and more than that. So what happens here? One atom. So as a result, what happens? The electron hole combines, electron hole combines. Like that, so many combinations exist. Then what happens is one electron and hole combines. Then the electron gets excited. Okay, then the electron gets excited. One electron gets excited, it gets excited. It goes from the lower energy levels to the upper energy levels. Again, come back to lower. It's done. And again, the second level, it also gets excited. So it goes from the lower energy level to upper energy level. Like that. So what we are doing is we are allowing to have more absorption. More absorptions, more emissions take place. More emissions takes place, more excitations take place. Then as a result, it goes from the lower energy levels to the upper energy levels. They come back to lower energy levels. This is what is happening in the semiconductor layer. All it happens is at the boundary. Okay, so there are most of the things that all be concentrated near the boundary, and here the as usual, like this is always a forward bias. The forward bias is what p-type semiconductor is connected to the positive of the battery, n-type semiconductor is connected to the negative of the battery. Okay, and we turn on in such a way that the radiation goes off, and what happens here? The transition takes between the layers, and then more absorption takes place, and then since the more absorption takes place, the electrons get excited. They goes to the upper energy levels, they come back to lower energy levels. All this happens within a fraction of a second. When you turn on, just it functions and gives off in the form of the beam. Okay, that is radiation. This comes out in the form of radiation. So this is what is said to be the semiconductor laser. Okay, here what we are using is the semiconductor is a very highly doped. Remember this, very highly doped. And you can sometimes it comes to your mind that, oh, what happens here in a PN junction, normal PN junction, no light comes out, and normally it functions, and current usually it passes the current. And here, what makes the semiconductor to have a laser? It will come to your mind that, oh, why it happens. Okay, I'll tell you. The reason is, see, in p-type semiconductor, generally we use germanium silicon, but here in this case, we use GaAs, gallium arsenide. And this gallium arsenide has got a special property of producing laser. Okay, and they have the capability to produce photon. Okay, once this absorption takes place, what happens? They get excited. Okay, the electrons goes to upper levels, and radiation comes out in the form of photons. Photon 1, photon 2, photon 3, photon 4. Like that, there are several photons coming up, and they line up to give the beam. Okay, a beam comes up, and that's what is said to be the laser. The laser and the semiconductor beam comes up. Okay, so we have here that's the one, and we have a different what is said to be here, the energy levels. Okay, the energy levels will also be there, and the semiconductor laser has got wide applications, of course. In the checkouts, you go to checkouts, and they read the barcode of the product. Okay, and immediately it will display. And so what happens is the radiation which falls onto this barcode and picks up, and then it will be giving up, okay, and displaying on the product details. Okay, so like there are several applications, of course. Okay, and then yeah, so we'll have in the next class we'll continue doing so. Okay, yes, thank you very much.
Thank you, sir.